Hello, and welcome to Week 3, Lecture 4 of CO 442-642 Graph Theory. Today we'll be talking about edge coloring multigraphs. So multigraphs, as you know, those graphs where you could have loops or multiple edges, so not simple graphs. Well, we can define edge coloring just for multigraphs. Color the edges of a multigraph so that incident edges don't receive the same color. Or equivalently, this would be taking the chromatic number of the line graph, because line graphs would be well defined for multigraphs. But as a note here, we will allow parallel edges, but not loops, because if you have a loop in a graph, then in the line graph, it's adjacent to itself. It creates a loop in the line graph, and then actually it wouldn't really be possible to color such things, as it would be incident with itself. So we'll do that, and then you get that the line graphs are actually simple graphs. So we'll just make that assumption throughout, and then we'll press on. So we're allowing parallel edges, but not loops. So then what can you do? Well, there are some trivial bounds from our old trivial bounds in vertex coloring, namely for the line graph, that still apply here. So delta of G is at most omega L of G, which is at most chi prime, which is in most delta L of G plus 1, which is in most 2 delta of G minus 1. So we have all those old bounds, as we established when we were first talking about edge coloring. What is true is, well, Koenig's theorem actually holds for bipartite multigraphs. So if you're a bipartite multigraph, then chi prime is equal to delta. And why? Well, the same proofs work. So remember, we give two proofs. The first proof was via Hall's theorem. That would work also for multigraphs. And the other proof was via these missing colors and Kent chains and things. And if you think about it, it too would work via multigraphs. Okay, so then where else can we go? So the next obvious question is, does Vizing's theorem hold for multigraphs? Can you get this delta plus 1? Well, no. So here's a nice example to look at. Take a triangle and kind of fatten up the edges by making lots of parallel edges. So here we do it where we'd have, say, the maximum degree over 2, and we'll take the ceiling on one of the pairs and the floor on the other 2, just to make sure that the max degree here is actually delta. So you tell me a delta, and I'll get this fattened triangle. And then what's the chromatic index of this multigraph? Well, it's 3 delta over 2, right? Because every pair of edges are incident. It really forms a clique in the line graph. So we can't seem to do better than around 3 delta over 2 by this example. Can we meet that? Well, yes. There's this nice theorem of Shannon that if G is a multigraph, then chi prime of G is the most 3 delta of G over 2 with the floor. So then the obvious question is, so we've improved on the 2 delta minus 1 to like 3 delta over 2, and then the obvious question is, can we do better? So maybe stop and pause for a moment. If you remember what I said just a couple seconds ago, you'd realize no, right? It's tight for this example, for the triangle above. So you can't really do better than Shannon's theorem. So the answer, we can't do delta plus 1. We can do better than the 2 delta, the trivia. We can do this 3 delta over 2, floor thereof. But let me ask another question. Can we do better? Same question, right? I mean, should you just be happy with Shannon's theorem? Is that's it for multigraphs? That's the answer? Or could we try to say maybe there's something special about such graphs? Maybe they have to look somehow like the triangle. Well, that won't quite be the case, but we will be able to say something. So namely how? We look to something called the multiplicity of a multigraph G, which we'll denote with this mu of G, mu being the Greek letter, is the maximum number of pairwise parallel edges in G. So in simple graphs, the multiplicity is just 1. There aren't any, pairs of parallel edges. Otherwise, we'll take it to be this maximum number. So in the previous example, the multiplicity of our kind of fattened triangle would be delta over 2 ceiling. So then what? Well, now there is a very nice theorem you can get that generalizes Vizing, and it was actually proven by Vizing back in 1964. And it goes like this: if G is a multigraph, then chi prime of G is at most delta of G plus mu of G. So you can get a delta plus the multiplicity. So again, for simple graphs, the multiplicity is always 1, so you just get Vizing's theorem for simple graphs. Delta plus 1 is the answer. But here, if you allow multiplicity 2, you get delta plus 2, and so on. And so in that way, you kind of are nicely generalizing Vizing's theorem. So this doesn't quite imply Shannon's, because your multiplicity could be larger than delta over 2. But actually, you can use it, and just a little argument to show that you can get Shannon's. And I'll do that in a little bit. But let me first talk about how would you prove Vizing's for multigraphs. So how do you prove this delta plus mu? Well, all the definitions carry over to multigraphs. So I really don't have to do much work. Kemp chains work, switching works, missing colors, Vizing fans. You look through all those definitions, they all work for multigraphs. Okay, well, what else with our proof of Vizing's works? The disjoint missing colors lemma that we spent so much time to with the Kemp chains and the switching and the cases, it just works for multigraphs. The same proofs work for multigraphs. So all that goes through. If you have a Vizing fan in a multigraph, and then you look at the missing colors, they'd be disjoint if you can't extend the color. All right, so that all works. So then what? Well, then we just need to tweak one little thing. So if you go back and look at my video on Vizing's and follow along, everything works until the very last step. So there's one little thing we got to change, one little calculation. So I'll just pick up from that point. Remember we had this finish, right? We were trying to prove Vizing's using our disjoint missing colors lemma. We took our maximum fan, we want to get a contradiction. So here let k, be the number of colors we're doing, be delta plus mu. And remember this very last step, this last slide, we had a maximal fan, and we looked at the colors x, which were the colors missing at the non-center vertices of the fan. And there we said x has to be at least n. Right? Because each color is, each vertex is missing a color, so great. But we can do better, actually. Because they're disjoint, now you'd actually have a better bound on x as a lower bound. Because if you think about it, if k is going to be larger than delta plus 1, if it's going to be delta plus mu, then every vertex has to be missing at least mu colors. So you'd get at least k minus delta times n, which is mu times n, missing colors. Okay, so what good is that? Well, then think about your fan. Now it's kind of weird because the fan has n leaves, but you could get in a bad situation where from V0 to Vi, there's actually mu edges there for each of those. So actually the number of edges, even though it's not used in the fan, the number of edges in the subgraph induced by the vertices of the fan could be quite large. There could be mu n of them. But one of them is uncolored, right? That edge E. So that means there's at most mu n minus 1 colored edges incident with V0 and another vertex in T. So we have mu n missing colors, and we have mu n minus 1 kind of colored edges around V0. So then what? Well, that means there is some color in X, which doesn't appear in those edges, call that alpha. And then that means since alpha, of course, is not missing at V0 by the disjointness, there has to be some new edge, En plus 1, which uses alpha. We can add that to our fan and again contradict the maximality. So that's all the same finish once you switch up that little bit of calculation. So instead of x is at least n and there are n minus 1 colored edges, is now x is at least mu n and there are mu n minus 1 colored edges. So that establishes Vizing's theorem for multigraphs, where you get delta plus mu. So then what about Shannon's theorem? Well, we can actually just go ahead and derive Shannon's theorem from this multiplicity version of Vizing's theorem. How does it go? Well, so we have to show that if G is a multigraph, then chi primes are most 3 delta over 2. So proof, we're going to proceed by induction. And then, as I alluded to before, if mu is actually, at most, delta over 2 floor, then it follows from this Vizing's theorem for multigraphs. You just have delta plus delta over 2 floor, and that's good enough. So we can assume that mu is actually big. That's bigger than delta over 2. Right? So somehow there is a pair. What does that mean? That there's a pair UV with a ton of edges. Let's have u be this pair with mu of G parallel edges with n's UV. And then here's the trick. So I'm going to show you a picture of this in a second. But let G prime be the multigraph obtained from G by identifying U and V to a new vertex W and deleting all the loops incident with W. So here's a picture of how this works. So we have our graph G, and we have U and V, and again they have a lot of edges between them. Mu of G, which is strictly greater than delta over 2. What does that mean? Well, since you have max degree delta, U has at most strictly less than like delta minus mu let's actually be less than or equal, but has at most delta minus u coming off one side, and most delta minus mu coming off the other side, which is going to be smaller than delta over 2. So then we're going to do this identification. So we take u and v and we identify them to a vertex w, deleting all those parallel edges between them. And you get a new graph. Now this, it's a multigraph maybe, because again, maybe you get some parallel edges coming off u and v. If they had common neighbors, that's fine. But importantly, what can you see is that the degree of w, so instead of z, that should be a w, small typo there, is at most 2 delta minus mu, which is at most delta, right? Because so you have delta minus mu on one side, delta minus mu on the other side, so you get 2 delta minus mu, and that's at most delta because mu is actually at least delta over 2. So we can do this kind of contraction and end up with a graph which doesn't have increased max degree. Of course, anyone else didn't actually get any higher degree because we didn't delete anything or add anything otherwise. So then, hence delta of g prime is the most delta of g. So by induction, we can get a 3 delta over 2 coloring phi. So we can get a coloring with the right number of colors that will color all the edges but the ones around W, right? So we've colored, if you back up, this picture, we've colored in G prime, now we need to get back to the coloring in G. So we have to add colors for those other vertices. So you just do a simple calculation, say works, this extends, because why does this work? Well, there's at most, this degree of W colors around, and then then we had to have mu colors. So I claim that actually there just are enough colors to extend this to mu. And that's clear because we'll have at most 2 delta minus mu, which is then at most 3 delta over 2 floor. So that's the proof of Shannon's. So if mu is small, just use Vizing's, and if mu is larger, you just kind of identify and then go by induction and just extend the coloring back to this thick bundle. So that's a very nice proof using the Vizing's, so not the original proof, of course, but very nice. And now what? Well, now I want to talk about, in my last little bit, where to go from there. So we have Shannon's, 3 delta over 2 is a nice bound. You have this delta plus mu bound. What more can be said about coloring multigraphs? Well, here's the crazy one. So I'm going to talk about something called the Goldberg-Seymour Conjecture, but let me introduce it and motivate it a little bit. So let P of G be the following very weird parameter. Let it be 2e g of x over x minus 1 ceiling, where x is any subset of vertices of G. What is that? That's a mouthful. Really, if you think about it, then what this gives you is you look at a set x, and then, let's say the set x is odd, then how many edges can happen in a matching when x is odd? It's x minus 1 over 2. So each color class in x can use at most x minus 1 over 2 edges. So how many colors would we need to color that subgraph? It'd be the number of edges over x minus 1 over 2, which gives you this, and then of course you could take the ceiling. So that will give you a lower bound on the chromatic index. So chi prime will always be at least p. And then here's this really beautiful conjecture by Goldberg and independently Seymour in the 70s, which says that chi primes for a multigraph is always at most the max of delta plus 1 and p. Right, so delta plus 1, that's our thing from Vizing's, our upper bound there. Remember, it's NP, complete or hard to tell between delta and delta plus 1. But what is it saying? It's saying for multigraphs, actually, you either get the delta plus 1 bound as an upper bound, or there's a reason why it doesn't color. So the reason it colors is just there's a subgraph with too many edges in it to effectively color. And that's what happens in the flattened triangle, right? This flattened triangle just has too many edges. So if that was living inside your graph, then that would be proof. There would be just too many edges. And it's saying that's the only reason. The only reason is this other lower bound coming from overfull subgraphs. And what else? Well, let me just mention this is equivalent to something called the fractional chromatic index. So Edmonds' matching Pauling-Boak theorem, which you probably know about if you took optimization, shows that the fractional chromatic index satisfies chi prime f of G being the max, this max of delta plus 1 and p. So you have this independent set-ish lower bound, and this is actually can be shown to be equal to something called the fractional chromatic index. which is the fractional relaxation of coloring for edge coloring. Hence, so the Goldberg-Seymour conjecture is really equivalent to saying that chi prime and chi f prime should be the same for multigraphs. So does that make sense? So we had this nice list coloring conjecture last time, where if you do list coloring or edge coloring, they should be the same. And here we're kind of saying for multigraphs, actually, it should be that the normal chromatic index, which seems really hard to get a control of, is actually equal to the fractional version. So, as a fractional program, the solution of that, we're using fractional bits of color. So I won't define that all because it's not so important here, but just one takeaway is that you have this really nice conjecture that says exactly what the chromatic index should be for multigraphs. And what's known about it, well, I'll just mention that actually one very useful thing is to generalize Vizing fans. So remember the definition of Vizing fans is you kind of have a star, a fan, and you want the edges that appear in that star to be missing at earlier vertices. And Vizing had shown that this disjoint missing colors lemma kind of holds for Vizing fans. So what else can you do? Well, there's a different way you could do this. It's called the Kierstead path, invented by Kierstead. Is instead of having a star, let's take our uncolored edge E and make a path out of it. So we just kind of switch the definition from U being V0, so always coming, the new edge is always coming out of the center, to being along a path. So you kind of grow a path where each new edge is now missing at some earlier vertex. That doesn't have to be the star or anything, or the center, but just missing somewhere earlier. So we'll call a Kierstead path, and actually Kierstead had shown the disjoint missing colors lemma holds for Kierstead path. So I won't state that because, again, definition was the statement was a little complicated, but saying if you don't have a coloring, you have a coloring with G minus E, but not with G, then you actually have disjoint sets of missing colors for all the vertices in the path. So that's very nice, right? We have fans, and they get this nice lemma for them, and we have paths, and you get a nice lemma for them. What else could you do? As hinted by the title of the slide, what generalizes a path and a star? Well, trees, right? So you can actually define something called a Tashkenoff tree, named after Tashkenoff, who introduced them. And what you do is you just kind of drop these conditions. Instead of U being Vj minus 1 or U being V0, you go forward and you just drop that. So you just say a Tashkenoff tree is one where all the vertices are disjoint, and each edge we're going to add just comes off of some earlier vertex. It doesn't have to be the last one, which would make the path, or the first one, which makes the star, just anywhere, with the property that the color of that edge, via Vj, was missing at some earlier vertex in the ordering. So you kind of grow a tree instead of a fan, a star or a path. And then what was proved? Well, Tashkenoff in 2000 showed what's now called Tashkenoff's theorem, that the disjoint missing colors lemma holds for Tashkenoff trees, generalizing both Kierstead and Vizing's results. So while Vizing's has a really nice proof, and Kierstead's also has a nice kind of similarly elegant induction proof, Tashkenoff's, while structural and inductive, is much more complicated. It runs about 20 pages. So it's a bit hard of a proof, but the main idea is actually, strangely, to make the trees more path-like. So you might think you'd reduce to fans, actually reduce to the Kierstead paths. And that's the key for proving that one. And then what's known about the Goldberg-Seymour conjecture? Well, in the little last bit, I'll just tell you what was proved about it. Well, same con as for the list coloring conjecture, proved that it holds asymptotically. So chi prime's at most 1 plus the low 1 chi prime f. So you're always, just a little bit of error away from that kind of lower bound of chi f prime. And actually, Planthold in 2011 had kind of improved this. It shows it's at most the max of delta plus 1p, that'd be chi prime f, plus the log of p. So even kind of improving on the error term, you just get this log for the that p function. Okay, so both of those results are nice. They're saying they hold asymptotically. We can improve the error term to just kind of a log, which is even better than the list coloring conjecture's error term. But they don't show that, it holds, right? It doesn't say, oh, if I was the flattened triangle, I actually hold. It has error terms in both. But actually, there was this very nice result of Shida in 2010 and independently by Chen, Yu, and Zhang in 2009. So they were both announced in 2008, showing that chi prime is at most the max of delta plus square root delta over 2, ceiling, and p. So what is that saying? A different way to say that is if you knew that p was larger than that number, so if p was like 3 delta over 2, like it is for the flattened triangle, then they're actually equal. So it says somehow if there's a subgraph that's 2 over full, then you are equal. Then that is the right number of colors. So this obviously then implies Kahn's result, because then they must, if we're larger than that, then they're just equal. And if we're smaller, the error terms at most square root delta from this. But it's going beyond that and showing exactly holds whenever p is too large. And this has been improved now in 2018. Myself and some co-authors, Chen, Gao, Kim, and Shan, to delta over 2 to the 1/3. So you can get that square root down to a cube root. And that's very nice. So the two theorems from the late 2000s were Shida used Tashkenoff trees and kind of arguments reminiscent of that proof of Vizing's. And then Chen, Yu, and Zhang use something called extended Tashkenoff trees. So by independent, really different. They're actually different proofs, very different methods, even if they both use Tashkenoff trees. And the idea here was you can combine the two and get it down to a cube root, which was very nice. So that's about all I wanted to say about the Goldberg-Seymour and coloring multigraphs. So again, the takeaways: Shannon's theorem, you get this 3 delta over 2, which is nice and tight. You can get delta plus mu, which is very nice. Same proof of Vizing's works there. And then, there's actually this big conjecture that tells you exactly what the number should be for multigraphs. Just like for list conjectured to be equal, here it's the fractional one where it's conjectured to be equal. And actually, it's been asymptotically proven, and you can even prove it kind of exactly if there's 2 over full of a subgraph, and that's been improved. And so we're moving closer to proving it, but it seems kind of hard, but that would be very nice. So that's all I wanted to say on edge coloring multigraphs. So that concludes our edge coloring for the week. Next week we'll be talking more about list coloring, but just vertex list coloring and coloring and list coloring planar graphs and graphs on surfaces. So until then, see you next time.